Guys, let's continue graphing trig functions. So remember in our last video we graphed sine and cosine. We learned how the amplitude changes those, and we've graphed some transformations using amplitude and also reflections. So we're going to continue translating sine and cosine functions in other ways today. So if you remember our basic sine function, we're going to start there with y equals sine x. All right, and let's remember, we're trying to graph this by memory at this point. You shouldn't have to be looking at values every time you graph just a basic sine or cosine function. Remember, you have 5 important points. For sine, you can plot your x-intercepts at the pi's. Remember, at the pi over 2's is where it hits its high and its low point. Remember, the first point it hits is high. It goes up to 1 at pi over 2. And at 3 pi over 2, it hits a low point of -1. Then we can fill in this wave. And this is our basic sine function. So in the last video, we took this and we stretched it or we compressed it using the amplitude, or we flipped it using a reflection. But remember, both of those changes did nothing to affect where the x-intercepts are. So today, we're going to look at changes that do affect those points and some changes that affect all the points. So the next thing I want to talk about is the period of the function. So remember, we talked last time a little bit about how the period of the sine function was 2 pi, meaning it takes a full 2 pi units to do one complete iteration of the wave before it starts repeating itself. Well, this is a period, let's call it the default period for the basic function, but I can actually change that. I can make this full iteration happen faster or happen slower. So we get this effect of shrinking it or stretching it horizontally. And we can affect that by adding a number into our equation. So remember, for amplitude, I put the a value, or I put a number right here, and that stretched it vertically. But this time, I'm going to put a value in here with the x. So we're making a change. I like to call this within the function because the number we're adding is within the sine function. It's in there with your x. So this b value, if you see it in an equation, what it does is it changes the period of the function. Now, we don't say that the period is b on its own, but b is affecting the period in a certain way. So to find the period of this function, it's always going to be 2 pi on top, because that's the default period, over b. So the period of the sine function is always 2 pi over b. Notice in your basic function, you could say there was a 1 there, the period being 2 pi over 1 or just 2 pi. But when b is a different value, notice it is going to change the period. So let's look at y equals sine of 2x. So your b value is 2, which means that your period for this one, 2 pi over 2, you can cancel out these 2's here. And what does it do? It essentially cuts the period of the sine function in half. So let's think about what that means. If a normal period takes 2 pi to do this up and down and back up, it means now I have to do all of that in half the time. So it's actually going to crunch it down, right? So when you look at b, what I want you to think is, okay, b is 2. I need to divide by 2. I need to cut everything in half. Now, remember, this is a horizontal change. It is not affecting where your high point is. So this goes up to 1, it'll still go up to 1. It goes down to -1, that's going to stay the same. Only amplitude can change that. All the period's going to do is going to stay as high and as low, but it's going to send it this way. So a horizontal change changes the x values, not the y values. So our period is pi now. We've divided it by 2 because b was 2. I want you to think about that 2, and your 0, 0 isn't going to change. Guys, we're going to stay at 0, 0, but every other x-intercept, we're going to divide that by 2. Everything has to happen twice as fast. So I'm going to say, okay, well, usually I go and I hit the x-axis again at pi. But since my period is cut in half, I have to hit it again by pi over 2. So I've taken this point, I've cut it in half, and it happens here now, pi over 2 instead of pi. Let's look at your other x-intercept. It happens at 2 pi. I have to cut that in half. This is our last, or our end point of the period, right? It's our last x-intercept. I have to cut it in half because I've divided by this b value of 2. So where it used to happen at 2 pi, it's going to now happen at 1 pi. So I x'd out this point on the original, but it's actually a point that is going to be on my function. So here's the x-intercepts of our new function. Cutting all of those in half. Now, let's think about your high and low points. Let me put this in a different color. This is our new period of pi where b is 2. So I fixed my x-intercepts. I cut all that in half. But you guys, I have to cut these in half too, not make the 1 into a half. That's not what I mean, right? I mean, I have to change the x value of that point. It used to hit this high point at pi over 2, but I have to do it in half the time. You guys, so I'm going to put in pi over 4. Think about the fraction here. It was at pi over 2. I need to cut that in half. Now we're at pi over 4. This is now going to be your high point. So I took it from here, I cut the x value in half. Did not change the y. And you guys, remember, we have 5 important points. I've changed 4 of them so far. The only thing I haven't fixed is the low point. You guys, our low point used to happen at 3 pi over 2. I have to cut that in half. Again, think fraction work here. When you have a 2 on the bottom and you want to cut it in half, all you have to do is divide by 2 again, which puts another 2 on the bottom, and we get 3 pi over 4. So this is now going to be your low point at 3 pi over 4. And let's look what it did to our wave. Okay, so what changed? The high points and low points are still at 1 and -1. That didn't change. But everything that used to take 2 pi to get through now gets through everything in 1 pi because everything was cut in half horizontally. Now, this is just one period of this function we graphed, sine 2x. Remember, if it keeps going, it's just going to keep going in the same fashion. So it's going to keep going like this. It's just going to be a faster wave. What we've done is we've increased the frequency of the wave. Okay, so you have a 2 here. The period, remember, isn't 2. It's 2 pi over 2. In this case, it's always 2 pi over b, and it cut it in half. So if I can cut it in half, can I make the wave longer? I definitely can. I am going to need more graph to do that. So give me a second. I'm going to make a new graph. I'm going to pause it so you don't have to watch me do all that. All right, guys, so I'm back. Look, it's magic. We have a new graph. Okay, so notice this graph is longer on the x-axis. I have taken this in units of pi over 2 like normal, all the way out to 4 pi. Reason being is because I want to graph the function y equals sine of 1/2 x. So when you see a number like 1/2, you say, oh, that's small, it should shrink it, right? Well, you guys, a 1/2 in this situation is actually going to stretch it because of the inverse relationship that b has with the period of the function. Remember, that's because b is on the bottom of a fraction when you calculate the period. So you guys, remember, the period is always 2 pi over b. And what's our b value here, guys? It's 1/2. So if I do 2 pi over 1/2, I've got a complex fraction here. Remember, if you're dividing by a fraction, what do? You flip and multiply, right? So 2 pi divided by 1/2 is like taking 2 pi times 2 over 1, or just 2 pi times 2. You end up getting 4 pi. So what did that 1/2 do? It actually doubled the period of the function. So let me graph basic sign again. You guys, what is basic sign? Intercepts at the pi's and high points at pi over 2, low point at 3 pi over 2. Here's our basic sine function. I've got that graphed. Now let's graph this new function where my period is 4 pi. So instead of taking all of these x values and cutting them in half this time, I'm going to double them. So dividing by 1/2 means multiplying by 2. So let's multiply by 2. Let's start with this high point here. I used to hit this high point at pi over 2, but I have to double that x value. So I'm not going to hit it at pi over 2. I'm not going to hit it till pi. I've doubled that value. All right, x-intercept. I usually hit it at pi, but I'm not going to hit it at pi. I have to double that. I'm going to hit it at 2 pi. What about this low point at 3 pi over 2? It's not going to hit at 3 pi over 2 because I have to double that. You guys, what's 3 pi over 2 doubled? So basically 3 pi over 2 times 2. Well, the 2's just cancel out. I'm going to hit this low point at 3 pi. And then my last point, I used to be all the way done, all the way back to the x-axis at 2 pi, but I have to double it, right? Because I'm doubling everything. You guys, it's going to happen at 4 pi. So let's see what this does to our wave. Okay. All right, so what did it do, you guys? It stretched it. So you guys, a fractional value here is actually taking your function and stretching it out. A larger value, like a whole number 2 or 3 or 4, is just going to squeeze it in together. Let's see, we haven't changed the amplitude today yet. All we've done is change the period, but we could do both at the same time. And you guys, I usually use examples with sine when I'm doing these transformations. It's because that's kind of the function we usually work with first. But the period and the amplitude, like you saw last time with the amplitude, everything works the exact same way with cosine. Remember, cosine just starts in a different shape. It's that trough or that valley, but everything else works the same. All the transformations work exactly following the same rules as sine. Okay, so I told you I wanted to do 2 things at once. So I want to find y equals 2 sine 2x. First of all, can I identify the changes from the basic sine function to this function? And you guys, you will have questions that don't have you graph, but they want you to identify the changes. So first of all, what's the amplitude of this function? Remember, the amplitude is just the number right here. If there was a negative here, remember, we wouldn't include that in the amplitude, it's just the positive. So the amplitude is 2. So let's find the period. Here's b. Remember, the period's just not just b, it's not just 2. It's always 2 pi over b. So we get our 2 pi over 2, and our period is pi. So it's cut in half, which means everything's going to be cut in half horizontally. But while we're cutting everything in half horizontally, we're going to be stretching by a multiple of 2 for the amplitude vertically. So you guys, I'm going to do this in one step. Again, you can do this and you can do each change in separate steps if you want to, but amplitude and period are pretty easy to put together. So start with your 0, 0. Do you know nothing has actually changed this point yet? It's acted like an anchor point for us. When we stretch, we keep it here, but we stretch it out, or we send it this way, but this has been an anchor. Amplitude, period, reflection, nothing has changed the 0, 0 point. We will change it, but these things don't change it. Okay, so obviously 0, 0 is fine. Remember, we're going off the basic sign, which is this red one. Okay, so usually we hit our high point at pi over 2. First, how does the period change that? It's cut in half. That means our high point has to be at pi over 4. So I'm going to hit the high point at pi over 4. Let's take our amplitude into account. I'm not going to hit 1 now because the amplitude is 2. My high point will be at 2. So we got the 0, 0, the high point. What's next? Our x-intercept used to be at pi. The period cuts it in half, so it's going to happen at pi over 2. And you guys, is the amplitude affecting this value? No, the amplitude doesn't affect. It still hits on the x-axis. But you guys, we hit our 0, 0. We hit our high point. We hit our x-axis again. It's time for the low point. Where does it go? Well, it used to happen here at 3 pi over 2, but it's going to happen at 3 pi over 4 now, which is between these two. Now, how low is it going to go? Your amplitude is 2, so it's going to be down at negative 2. We're almost done. We've got 4 of our 5 important points. 0, 0, high point, intercept, low point, back to the intercept. Where is it going to be? I think you can see at this point that it's going to be at pi. It used to end at 2 pi, now it ends at pi. The amplitude, again, doesn't affect that. And here we get y equals 2 sine 2x. The period b being 2, cut it in half. It happens twice as fast as normal. The amplitude stretched it by a factor of 2. Now it goes up to 2 and down to negative 2. I could reflect this pretty easily. We could put one of those in there. You guys, so let's go purple. I want to graph y equals negative 2 sine 2x. It should be pretty easy from what I already have. What's the only difference? Well, it's this negative. Does this affect the amplitude? No, the amplitude is still 2. The period, well, because b is 2, we already calculated it, and the period is pi. So these two things are the same. But what does the negative do? Let's remember, it flips it over the x-axis, right? So this is going to happen upside down. You guys, where we used to be at a high point here, we're going to be at a low point now. Where this low point was is now going to be the high point. So this time we're going to start down and end up. So you guys, here is 2 sine 2x. Here's negative 2 sine 2x. Just to recap, the red here was our basic y equals sine x. What was the purple? Oh yeah, it was y equals sine 1/2 x, where we doubled the time it took to get through one iteration. So that's cool. We've got a lot of changes we have to keep track of now. We've got reflection, which is easy. It's just flipping it, right? Amplitude, also pretty easy, stretching it vertically. Period, not as easy, but I can pick it out of an equation. You guys are going to be happy with me because you'll notice on your homework, you actually don't have any graphs where you have to change the period. It's probably the hardest thing to graph, so you don't actually have to graph it. What you do have to do is be able to look at an equation and tell me what the period is. So if this is 2, you have to be able to tell me that the period was pi using the formula here, 2 pi over b. So yes, can you pick out the period? Can you say that it's 2 pi over b, but no, you don't have to graph it. I graph it for you because I want you to see the visual effects of the period, but you don't have to recreate that. You definitely will have graphs where you change the amplitude. You will definitely have graphs where you have to reflect. And you're going to have graphs with 2 other changes, and that's what I'm going to talk about next. All right, so I'm back, guys. Notice my graph has changed a little bit. I've still got the positive x-axis the same in units of pi over 2. I went out to 3 pi this time. But notice I've got some negative side of the graph here, and we're going to utilize that when we make these next changes. Okay, so let's work with cosine this time. Since we've been working with sine for a while, we need to remember how to graph cosine. So I'm going to first start by the basic y equals cosine x. So remember, cosine actually starts at its high point. So here it's up at 1. Pi over 2 is an intercept. Pi is -1. 3 pi over 2 is an intercept. And at 2 pi, we're back up to 1. So here's basic y equals cosine x. And let's talk about how I want to change it. I'm not going to change the amplitude or the period of this function. I'm not going to reflect it. You guys, all of those changes either change the direction or the shape of the wave. What I'm going to do now is I'm actually going to pick this up and move it somewhere. I'm going to maintain shape, maintain direction, just pick it up and move it left or right, and up and down. Let's start with up and down. It's the easier. So you guys, I want to do what's called a vertical translation, or a vertical shift. I think that's what Alex calls it. So let's talk about a vertical shift. In an equation form, it would look something like this. Maybe I'll have y equals cosine x plus 2. Notice this 2 is not where amplitude goes. It's not where my b value goes to change the period. It is separate, totally separate from the function. It's just sitting here on the outside. It could be in the front or the back, but it's not part of your cosine term. So I have this plus 2. What do you think that's going to do to my graph? Well, you guys, this is going to be a vertical shift. And it's going to go 2 units one way or another. You guys, what do you think plus 2 is going to do? Yeah, it's going to send it up 2. Or 2 up. Apparently that's how I like to write it. All right, so that means every single point goes up 2. It's a real easy shift. So take this point here, move it up 2. So now it's at 3. Take your intercept, move it up 2. Take your low point, move it up 2. Take your intercept again, move it up 2. Dang it, there's not enough room. So I gotta erase stuff. You have that written down if you're taking notes. I'll probably write the equation again, but I do need to take this high point here and move it up 2. So have I changed shape? No. Have I changed direction? No. All I've done is pick up this exact thing and move it up. And you guys, again, I've been graphing just one period of these functions. Remember that they continue in both directions. But I've just taken the whole thing and I've moved it up. So this was y equals cosine x plus 2. What do you think would happen if I wanted to graph, where's my red mark? Hold on, fell on the ground. What would you think would happen if I want to graph y equals cosine x minus 1? You guys, can you pick out that this is a vertical shift? This vertical shift is -1, or you're going 1 down. So I can't remember exactly how Alex wants you to put this. I don't think you can put the word up or down. I think what it would look for is the negative on it. So you would actually put -1 in there. For this one, you would just put +2. All right, so from your basic version, this time I'm shifting every point just down 1. So down 1, down 1, down 1, down 1, and down 1. So there is your vertical shift up and your vertical shift down. Again, it's probably the easiest thing that we do with these functions. So we've got that. Let's talk about a different kind of shifting. What if I want to pick it up and move it left to right? So I've made a new graph because that one was getting a little crowded, but this is the same window that I had before. I've graphed the basic y equals cosine x again. Now we're going to talk about how to shift it left or right. So I want to graph the equation y equals cosine of x, x plus pi. And let's think about that. So what is different about where I put this number? Did I put it on the outside where it just said plus pi or minus pi? No, it is a change within the cosine term. It's not here where b goes. It's not here where a goes. It's not out here where the vertical shift goes. You guys, it's in here with the x, but it's added. It's going to be added or subtracted here. So you guys, this value, so you'll have x plus this value. A lot of times we call this c, or it could be a minus there. This is what gives us our horizontal shift, or what we call the phase shift. It's hard to call something a horizontal shift when you're on a continuous wave function because, let me give you some insight on that. So remember that this goes on forever in both directions. And it would be over here, something like that. So to think about picking this up and moving it left or right is kind of hard to think about because there's already, it goes on in both directions. So you can move it to left, to the right, all you want. It's not going to change where it starts and ends because it really doesn't start and end. We call it a phase shift because what it does is we're changing the phase of the wave. Where it used to start, when it used to hit a high point at 1, it'll just hit it somewhere else. It might move every point to the left or move every point to the right, but we know that it still goes on in both directions, just changing where the high points and low points hit. So our phase shift, it has to do with this, but it is more than that. You guys, the phase shift has a formula, just like the period did. Remember how the period was always 2 pi over b? Well, the phase shift is going to be, sorry, I'm going to call this c for a minute. You guys, if this value is c, your phase shift is always c over b. Notice we have that over b again. We're always dividing by that b value anytime we're doing some horizontal change. So in this case, our c over b would be pi over, well, isn't b just 1 in this example? So it would be pi over 1. So I would say my phase shift is pi, but that is not enough to tell me which direction, right or left, I'm going to go. You guys, when we are shifting horizontally, I have to think about this inverted. It's a backwards thing. So you guys, if I have a plus here, this plus indicates that my shift is actually to the left. So when I have a plus in that spot, it means that I'm shifting to the left. When I have a minus in that spot, I'm shifting to the right. In ALEKS, when you're answering these questions, remember it's not going to say left or right. You're going to use a minus to indicate that it's shifting to the left, and you're going to use a plus to indicate that it's shifting to the right. So I don't want you to get confused about it. What I do want you to do is take whatever is here and switch the sign. So for our phase shift, because this said plus pi, our phase shift is going to be, you would write in minus pi. No, it's not a minus there, but this minus indicates that we are shifting to the left. Okay, so let's put that in action. You guys, phase shift of minus pi or pi units to the left, just like with the vertical, we pick it up and we move it. You guys, every single point that we've graphed, we're going to move to the left, pi units. So you guys, this used to happen here at 0. Remember, we're moving left, so it's going to happen at pi. Notice I went pi units to the left. Now my point is here. Go to your next point. Pi units to the left. Sometimes it's hard, you guys. Just remember, that you're in units of pi over 2, so you're in half pies. If I want to go a full pi units, remember that's 2 of these. So pi units to the left. Now we're here. Take your next point, do the same thing. So it's at pi. If you take that pi units to the left, it's going to hit on the y-axis now. So we're here. And then I'm going to shift this one over and shift this one over, pi units to the left. I'm drawing these arrows. I don't know if they're confusing you or not. They might be confusing. Next time I won't do the arrows. But let me draw that in. Let's show you what I got. It'll be more helpful if you put it in. So what we did, we took this basic cosine, we picked it up and we moved it over pi units to the left. Because this was a plus pi, our phase shift was C over B. Remember, if you have a B value that's not just 1, you will have to put that on the bottom. And then you note that the phase shift would be minus pi because the minus indicates that it's going left. So I know this is a lot to work with, guys. Let's do another phase shift. Let's go to the right this time. Okay, so let me graph this time. Y equals cosine of x minus pi over 2. You guys, I'm not going to have us graph one where we have a period change and a phase shift change. You won't have to graph ones like that. So I'm doing these separately. This is just going to be a phase shift change. All right, so x minus pi over 2. All we're changing is the phase shift. Remember, the phase shift is always C over B, this being your C value. You know where B is, it's right here. For us, it's 1 in this case again. So I get pi over 2 over 1, which is just pi over 2. But you guys, let's think about which direction it's going. So you guys, if there is a minus here, it means we're actually going to shift everything to the right, which means even though there's a minus here, when I write my answer for phase shift, I'm not going to put a minus here. It's going to be a positive pi over 2 because that indicates that we're going to the right. So I've switched the sign again. All right, so let's graph it. Don't forget, we're starting from this basic version. We're going to shift everything pi over 2 to the left. So this time, I start here, send it to the left. Next point, send it to the left. Notice I'm not going as far this time. I went a whole pi units that way. I'm only going pi over 2 to the left. So we're here and we're here. The low point is now here. Intercept now here. High point now here. And graph it. So the purple, I went pi units to the right. Back to the beginning, the red went pi over 2 units to the left. Remembering in both cases, these functions are still continuing on and on and on. It's just where their waves are happening has changed. So that's why we don't just call it a horizontal change or translation. We call it a phase shift. Okay, so that's a phase shift. Remember, again, this works for sine also. Same idea, same everything. And you guys, that is the last of our changes. So what did we have? We had amplitude, we had reflections, we had vertical shift, and we had phase shift. Those are the ways, oh, and we had the period. I forgot to mention that. Those are the amplitude, period, reflection, 5 ways that we can change a sine or a cosine function. So you do have some graphing. You guys, I tried to keep the graphing pretty basic. You'll have to graph the basic sine and cosine. You'll have to graph some with amplitude changes, some with vertical changes, and some with phase shift changes. Remember, I didn't make you change the period when you actually have to graph the problem. I think there might be a couple that have two different changes, like maybe a reflection and an amplitude, like I did in the first video. And I'm pretty sure I gave you a couple that you have to change the amplitude and phase shift it. Both of those are easily combined steps, so I think you can get through them. But let me go back to those equations, because you actually have some you don't have to graph at all. All you have to do is identify the changes in the equation. So I'm going to give you some examples. Okay, so what if you have something like this? This is a big equation, right? You guys, every kind of change I could make, I have made in this equation. Would I make you graph this equation? Definitely not. This would be trouble. This would be trouble. This would be somewhat trouble for me. So anyway, so we're not going to graph this. What it's going to do is going to ask you the important things. It's going to ask you the amplitude. Be careful, there's a negative in front. Do I consider that in my amplitude? No, I don't. Amplitude is this value here. So I would write positive 3/4 as my amplitude. It's going to ask what is the period of this function. Remember where period comes from. It's just this value with the x, that b value, and I take that b value and I do 2 pi over b to find the period. So I get 2 pi over 3, and I can't really reduce that, guys. The period would be 2 pi over 3. All right, it'll ask, what about the vertical shift? You guys, it's a -7, so you would write -7 as your vertical shift because that minus is indicating that it's going down. Remember, with the vertical shifting, you bring the sign with it, you don't change it. Unlike the next piece, the phase shift, we do change the sign. Don't forget, it's not just this value, it's this value over b. So your phase shift, if this is c over b, we would get pi over 3. So we have a phase shift of pi over 3, but does it go left or right? You guys, this plus tells me that it actually goes to the left. So remember to switch the sign on that. Give it a negative, indicate that it's going to the left. So you guys, you will have these questions and you will have to pick out all of this information. Again, this would be a bear to graph, but picking out the changes should not be that hard. You'll have some that say sine here, you'll have some that say cosine, but this is how you do it. I don't think it asks about the reflection. Just if there is a negative there, make sure you don't put it in your amplitude. All right, so you have questions like that. Now I'm going to pause this again. I'm going to put a lot of different graphs up here to teach the next little thing. It's just going to take me a minute. Okay, so I'm back. Now, notice I've got some graphs that are already pre-made for us. You guys, this is y equals tangent x and y equals cotangent x. You don't have to graph the other 4 trig functions. So tangent, cotangent, secant, cosecant. You won't have to graph those, but what you will have to do is you have to know the domain and the ranges of these. So that's why I have them graphed. I'm going to talk a little bit about that. Let's start with the tangent. So here's what you need to know about tangent. Notice on this graph, there are some dotted lines. You guys, these are what we call asymptotes on a graph. You should have heard that word before, probably in algebra. It just means the graph is undefined there. The function tangent doesn't exist at these points. So you guys, that changes your domain. Remember, domain are the x values of a function. All the x values of the function where they are defined. So notice for tangent, our domain looks like all these x values are fine, all these are fine, and all these are fine, but it has these breaks where it stops. So you guys, what we say for the domain And even before I get into that, you guys, y is tangent undefined at pi over 2. Remember, tangent is always y over x? Well, the x value is 0 at the pi over 2. So pi over 2, 3 pi over 2. So if you have that 0 on the bottom, that's what's making that undefined. So your domain, so the domain of this function is going to be all x values except for values of the pi over 2's. So we have to find a way to say that. So what we say for the domain is I'm going to say that the domain here is all real numbers except for, and I'm going to write it and then I'll explain why it's written this way, except for odd integer multiples of pi over 2. Informally, I usually say the pi over 2's, and that makes sense to us. But in a more formal way, I say all real numbers except the odd integer multiples of pi over 2. So odd integer multiples. What's an integer? First of all, that's just your counting numbers, right? So whole numbers, 1, 2, 3, 4, 5, or they could be negative, but they're whole numbers. So an odd integer would just be the odd numbers, right? So 1, 3, 5, 7, or the negative versions of those. And when you put those odd numbers with the pi over 2, what do you get? You get numbers like 1 pi over 2 and 3 pi over 2, and you would get 5 pi over 2 and 7 pi over 2. But because it's an odd number on top, it makes sure that it's still a pi over 2 value. So this is what makes this the pi over 2. So the domain of the tangent function is everything, all real numbers, except odd integer multiples of pi over 2. Now let's look at cotangent, because it's different. Notice your cotangent function does have those asymptotes, but they're in a different place. Remember, cotangent, if tangent is y over x, remember cotangent is x over y. So cotangent is going to have problems, or it's going to be undefined everywhere where y equals 0, which is going to be different places than where x equals 0 that gave us a problem here. Notice where my asymptotes are. Where is it undefined? Well, at 0, at 1 pi, at 2 pi, at 3 pi, 4 pi, it's at the pi's. So this one has a problem at the pi over 2's. This one has a problem at the pi's. So how would I say the domain of cotangent? Well, again, I would start by saying, well, it's all real numbers except for, and you guys, I don't have to use the word odd here because I'm not trying to get pi over 2's, I'm trying to get whole numbered pi's. So what I say is all real numbers except for integer multiples of pi. So what does it mean to be an integer multiple of pi? It means to put an integer in front of pi, a whole number in front of pi. So 1 pi, 2 pi, 3 pi, 4 pi, negative pi, negative 2 pi, negative 3 pi. Notice all of those are integer multiples of pi. That's where cotangent's going to have a problem. So when you're doing these problems, I'm pretty sure you select from a drop-down list. It'll say like, what's the domain of tangent? And you pick the line that's true. So you'll pick on tangent the one that says, oh, everything except the pi over 2's. For cotangent, the domain, oh yeah, everything except the pi's. What about the ranges of these? Because we have to know their domain and the ranges. You guys, tangent and cotangent are the best on the range. You guys remember that range is the y values that the function takes on? And look at the arrows we have on these graphs. You guys, these arrows indicate that it goes down forever and that it goes up forever. And that means that tangent takes on every single y value from negative infinity to positive infinity, which means its range is all real numbers. So you guys, the range of tangent is all real numbers. What do you think about the range of cotangent? Well, it's exactly the same. They don't have the same domain because their asymptotes are in different places, but the shape, the way the arrows go all the way up and all the way down is the same. You guys, the range for cotangent, all real numbers. Those are probably the easiest ranges we have. So here I've got some graphs of cosecant and secant. Again, these are not things that you have to graph or recreate on your own, but you do need to know the domain and ranges of these, just like tangent and cotangent. So let's start with cosecant. You guys remember cosecant is the reciprocal function of sine. So you'll notice I've got some dotted lines here. The vertical dotted lines are asymptotes, just like tangent and cotangent had. Cosecant does have some asymptotes, but this dotted graph, this dotted wave here, this is the sine function. I like to graph the sine function in with the cosecant function to see how they're related, to see what it means visually to be a reciprocal of another function. So you guys notice the sine I've dotted in, the reciprocal function of that cosecant, look how it meets. You guys, they have points in common at the 1 and -1 because you know the reciprocal of 1 and -1 are the same, 1 and -1. So it makes sense that they would meet at points. Let's see where their asymptotes come from. So you guys, we have an asymptote at pi, also at 0, and also at 2 pi. You guys, these are places where sine equals 0. So if sine equals 0 and you flip it over, you get a 0 on the bottom. That's why cosecant is undefined at those places. So when you're talking domain of cosecant, you guys, it's going to be everything except what? You guys, where are these asymptotes hitting? They're at the pi's, right? So all except the integer multiples of pi. So that is just like the domain of cotangent, and that's a good way to remember it, guys. Cotangent and cosecant have the same domain. Both of them are everything except the pi's. What about the range? You guys, the range of cosecant is kind of interesting because notice it starts here at 1 and it goes up forever, but then look at all this space. It doesn't touch. It never touches this center section where the sine function actually touches. You guys, and then down here at -1, it goes down forever from there. So our range is going to be 2 intervals. You guys, you're going to have a range from -infinity up to -1 with a bracket because it includes -1. So what part of the range am I getting there? I'm getting everything down here all the way up to this, but then I have to skip this part in the middle. So what I do is I use a big U. We say that's a union. I'm saying the range is this interval unioned with another interval. And so we skip this area and our next interval starts at 1. Notice I bracketed it. It includes 1 and everything above 1. So it goes from 1 to positive infinity. So you guys remember when I talked about the range of sine, it was between -1 and 1. It was a bracketed interval from -1 to 1. Notice that cosecant has a range of everything else. So sine gets to take up this area. Cosecant, its reciprocal, takes up everything else. So it's like the reciprocal functions have complementary ranges. Sine takes this part, cosecant takes everything else. So that's a good way to think about the range of cosecant. Okay, so let's talk about secant. Let's talk about its domain. What graph do I have dotted in here? You guys, this is cosine, right? Cosine and secant are the reciprocal pair there. So again, it's very similar to this, just using cosine instead. You can see where they have values in common, but notice everywhere everywhere where cosine is, secant takes up the rest. Where is secant undefined? So what do I have to exclude from my domain? It's the pi over 2's this time. It's places where cosine equals 0, so when I flip it over to get secant, it doesn't exist. So, well, my domain for secant is all except, you guys, it's the pi over 2's. It's the one where I have to say all about the odd integer multiples of pi over 2. What domain does this have in common? You guys, that's the same as tangent. So secant and tangent have the same domain. Cosecant and cotangent have the same domain. That's a way you can remember. What do you think about the range of secant? You guys, don't you think it's probably the exact same as the range of cosecant? Even though it happens in different places. Look, it hits 1 and goes up. It skips the area from 1 to -1 in the middle, and then it gets everything from -1 down. So you guys, this range that I have written for cosecant is also the range for secant. All right, guys, so we already talked about the range of sine and cosine being between -1 and 1. The range for these cosecant and secant functions is here. Remember, the range for tangent and cotangent are both all real numbers because they hit every value. And then the domains. You guys, the domain of sine and cosine, they didn't have any asymptotes. We didn't see any of those places where they're undefined. So for sine and cosine, the domain is all real numbers. For cosecant and cotangent, your domain just excludes the pi's. So everything except the pi's. For tangent and secant, your domain is everything except the pi over 2's. So again, you'll have questions where you have to answer, it's kind of a multiple choice situation on domain and ranges, but here they are for you. And you guys, luckily that concludes our graphing section.